And everybody remember this, and looking at all the grey heads that I see in the audience. But this was 1957 when Sputnik was launched up there. We thought it was something fantastic and everything. And look, the leaps and bounds that we've gone since then is absolutely amazing with everything that's gone up there. And this, to me, is science fiction. This was science fiction when I was a kid looking up at this happening. But the next step is this. This is our little AirSat, which Laura was involved in getting it up there into space. So with that, Laura, you could.
My name is Laura, and I am currently a third-year PhD student here in University College Dublin. My office is directly below us, and I am supervised by Dr. Antonio Martin Carrillo, and I work with Dr. Lorraine Hanlon here in UCD on AirSat 1 and on my PhD. So the first thing I'm going to do is I'm going to talk a little bit about my own research first, and then I'm going to fill you in on what's happening with AirSat 1 at the moment. So I'm just going to go through just a little bit of the basics of like how stellar life cycle works. So a star is born from a dust cloud. So out in space, there are these massive clouds of dust and particles and gas. And what happens is these particles slowly start to clump together, and these clumps crash into each other, and slowly they become even larger. And the force of gravity gets stronger as these clumps get bigger, and eventually it starts to collapse. It gets hotter because it keeps rubbing up against other gas particles, so it creates heat through friction, and eventually we create a protostar. So this is how the star is born. So this protostar continues to suck up all of the dust, all of the matter that's present in these dust clouds, and eventually will create a fully formed star. So the mass of the star is what governs how the star lives and dies. So, and then the amount of stuff that is in these molecular clouds governs whether we're going to get a low mass star, which you can see in the yellow there, or a high mass star, which is the blue. So a low mass star has a relatively quiet life. It lasts for maybe greater than 75 million years, so it lasts a really long time. It burns all of this fuel, hydrogen, helium at the centre of the star, and eventually it sheds its outer layers gently, forming planetary nebula. And at the centre of that planetary nebula is a small star called white dwarf. So it's shed all of its outer layers, so you can see the kind of a gas cloud surrounding the star. And this white dwarf will very slowly fizzle out into a brown dwarf and kind of flicker away like a candle. On the other side of things, we have a high mass star, and a high mass star has a much more exciting life, but however, it is much shorter than a low mass star's life. So a high mass star will last maybe less than 1 million years. So in the centre of this high mass star, we're constantly burning elements. So I think Carl Sagan had a quote that we are all made up of star stuff, and that is true. So these high mass stars are constantly burning elements at its core, and it's burning heavier and heavier elements. So all of the heavy elements like gold, silver, iron, everything was synthesized at the center of the star. So these high mass stars eventually run out of energy, so they don't have enough energy to synthesize the metal at the center of its star anymore. So eventually what happens is when it runs out of fuel, there's no pressure, outward pressure, balancing out the gravity that's pushing it in, and it collapses in on top of itself and explodes into what we call a supernova. And what's left after that supernova is either a black hole or a neutron star, which is a very dense star with a really strong magnetic field. So what I focus on in my PhD is these stages of the star's life cycle, where we have a supernova explosion and the production of new stars. So with that, I'm going to talk a little bit about supernovae. So supernovae are the brightest objects in our universe, and there are two main types. We have a type 1a supernova, which you can see on the top right-hand side. So this occurs when we have our little white dwarf star, and it's very close to a larger star. So what the white dwarf is doing is sucking all of this matter from this larger, heavier star. It eventually gets too full, so it reaches what we call a critical mass. So it's almost like you're having dinner, you've had a little bit too much and you're full to the brim. And this star explodes into a type 1a supernova. And the second type of supernova is called a core collapse supernova. And this, what happens here is the nuclear processes stop at the center of the star, it collapses in on top of itself, and then explodes outwards in a core collapse supernova. So we have different types of subclasses underneath the core collapse supernova called 1b, 1c, and type 2. So these supernovae, they don't last forever. You don't see them all the time in space like a star. They only last for a few days and can last upwards of a few years, the brightest ones do. So again, the type of supernova that I focus on is the core collapse supernova. And there's a specific, very rare subtype of core collapse supernova that I look at. And they're called broadline type 1c supernovae. So you're probably thinking, we have a core collapse supernova. How do we distinguish between the 1b's, the 1c's, the type 2's, all of the different types of supernova? So broadline 1c supernova has no hydrogen or helium present. So what's happened is these outermost layers, so a star, when it's about to die, when it's produced all of these chemical elements, has layers. It's almost like an onion. So at the center we have iron, which is very stable, and it's very hard for a star to break that down further into a heavier element. And then we have the lighter elements on the outside. So what happens is these really strong stellar winds rip off the outer two layers of the star. So before the supernova happens, we have no hydrogen or helium in its outermost layers. So we also see very high ejective velocities when it comes to 1CBL supernovae. So to put this into perspective, it can be anywhere between 15,000 and 30,000 kilometers per second. So that could be upwards of 10% of the speed of light, which is very fast. And these high velocities lead to kind of broadline features and what we call spectra. So you can see examples of supernovae spectra on the left-hand side. So these kind of images that we take show us what elements are present in a certain star or a certain supernova. So you can see down at the bottom there. Down at the very bottom, you can see the type of spectra that we see with the type 1 CBL supernova. And you can see it's super smooth in comparison to the other subtypes. So that's how we can tell a 1 CBL from the other types of supernova. As I said, they're very rare. We only classify approximately 20 per year, which is very, very low in comparison to the thousands of type 1A supernovae we classify per year. And the most interesting thing about these supernovae is they're associated, and they're the only type of supernovae that are associated with gamma-ray bursts. So you're probably wondering what GRBs are, or gamma-ray bursts are. And gamma-ray bursts, so as I said, the supernova is the most energetic, is the most brightest thing in our universe. Gamma-ray bursts are the most energetic things. So gamma-ray bursts eject matter in the form of jets, so really tight collimated jets, the poles of the stars you can see in the GIFs there. And they shoot them out at speeds that are ultra-relativistic, so super close to the speed of light. So you thought that it was quick with the supernova. This is even more fast. It can happen in the blink of an eye. It's unimaginable how much energy and how the speeds at which this matter is being ejected out into space. So again, you probably thought supernovae, they happen really quickly. These happen even more quickly. They can some gamma-ray bursts last from a few milliseconds. You could close your eyes, open them, and a gamma-ray burst would have happened, and you wouldn't have even noticed it was there. And some of them, if we're lucky, they'll last several hours, and you can get really good data on that. So again, we have two types of gamma-ray bursts. We have mergers, where we have two neutron stars, and they're orbiting each other, and they collide to form a gamma-ray burst up on top. And then the GIF on the bottom is a collapsar GRB. So they occur when, again, a massive star collapses in on top of itself and ejects its matter out in the form of jets. So the type of gamma-ray bursts that I study are collapsars. So they last a little bit longer. So the mergers will be very quick. They'd be the gamma-ray bursts that last a few milliseconds, really, really quick things to happen in space. Whereas collapsars, they can last up to several hours. But again, it's very quick on the timescales of the universe. So now that I've talked and given an overview about what supernovae are, what gamma ray bursts are, you're probably wondering, how do we even look at these kind of things? What do they look like? So the first thing that we do is we look at telescopes on Earth. We use telescopes on Earth, and we use telescopes that we put in orbit on satellites. So on Earth, we can look at optical and radio waves. So we can observe these supernovae in these two different forms of electromagnetic radiation. However, we can't see any X-rays or gamma rays coming from space from Earth, because the atmosphere is protecting us from all these really harmful radiation. Because if we didn't have this protection from gamma rays and X-rays, we'd constantly be irradiated with this really harmful radiation. We wouldn't be able to go outside. So what we have to do is we send these detectors up in space, up above this atmosphere, to be able to detect this form of radiation coming from gamma ray bursts and supernovae. So using these telescopes, we can take images like this. So it's really important that we study astronomical phenomena in all different forms, in all different types of electromagnetic radiation. So if you look at the far right, you can see an image taken by NASA's Fermi telescope in gamma rays. So you can see there's a really bright flash and then it disappears. So those are the gamma rays coming from this particular gamma ray burst. So this gamma ray burst is the brightest gamma ray burst we've ever detected, hence why we have it imaged in all of these different electromagnetic radiation, types of electromagnetic radiation. And then we have an image in X-ray. Again, you can see the kind of blue, kind of circular one on the far right. It's really bright in this image as well. However, if you look at the very large telescope, the VLT in the middle, that's visible light. You can barely see the gamma ray burst in this one. It looks like a star. Then if you look using the James Webb telescope, you can barely even see it again in infrared light. And then in radio, it's just a blob. So this highlights the importance of how different, of looking at it in different forms of electromagnetic radiation, and how different it can look at different sides in different types of light. So again, once we have the images, what do we look at then? So there are two main ways in which we present astronomical data, and we kind of extract meaningful information from astronomical data, and that is through light curves and spectra. So here I have an image of a picture of a light curve that I created myself of a specific type of 1CDL supernova. And this graph up on the top right shows how the brightness of this transient, of the supernova, is changing with respect to time. So you can see that it increases up really bright and then it diminishes again and fades away into the sky. So these very simple graphs can tell us a lot about what's happening with the supernova. Things like when it's at its peak brightness, how long it takes to get to that peak brightness, the duration of the entire supernova. So you can see that that supernova lasts maybe 40 days. And then we can actually extract information about how much energy is released in the entire explosion. And then with our spectra, I've mentioned that before, so our spectra shows us what kind of elements are present in a gamma ray burst or supernova. And it tells us about the chemical composition, so what elements are present. It can tell us how far away the supernova or the gamma ray burst is. So it's a quantity that we call redshift, is what shows us how far away something is from us. We can use the lines that are produced by elements to basically see how far away things are in space. And it can also tell us about the velocity of different of the matter that's being ejected into space. So those are the two things that I mainly used in my research to study supernovae and gamma ray bursts. So I'm missing a slide. So we have a few problems when we're studying gamma ray bursts and supernovae. So as I've said before, they sometimes, in very, very rare occasions, we have a gamma ray burst and a supernova happening at this exact same time. And the first of these kind of phenomena was detected in 1998, so very recently. And so since then we've only detected properly 13 of such events. So there has been more happening, but we haven't had enough data. We haven't had good enough data to actually study them in depth. So there's only 13 at the moment that we can really study and we can really draw in scientific conclusions from. And there's a number of reasons why we're not getting the good data. We're not getting good enough data that we can use to draw more science from. And one of the problems that we need to solve at the moment is how we classify the type 1 CBL, the really rare type 1 CBL supernovae. And that is one of the problems that I'm addressing in my PhD. So the first project of my PhD is all to do with how we can better classify these types of supernovae. And I'm actually just finished writing my first paper on this. So we need really early observations of supernovae and gamma-ray bursts to extract meaningful science from it, because they happen really quickly. So, you know, gamma-ray bursts, they only happen over the course of a few hours. Supernovae fade over the course of a few days. So we need to be very quick and very precise with how we're detecting these things. But we need to classify them first. So 1CBL supernovae are classified very late. So almost too late. So when you look at the light curve that I was showing you previously, it's after the peak, after it's at its brightest, we're classifying it. And at that point, we've missed the start of it, where the GRB is going to be. Often 1CBLs are misclassified. So you might look at a supernova in the sky and someone might say, that's a 1A supernova. So we don't bother with it anymore. And then a couple of days later, when we have the full light curve, we have all the end of the data, someone says, oh, it's actually 1CBL. And then again, at that point, we've missed the start of the supernovae and we've missed the potential GRB. And some type 1CBL supernovae, they're not classified at all. So there are tens of thousands of transients that we detect in the sky and we can't associate with classification with it. So these are the kind of problems that I am attempting to address in this project. So you're probably wondering, how can we help classify these? Well, first we need to look at what the telescopes are looking at. So a single telescope can obtain almost more than 4 terabytes of data per night. That is way too much for a human mind to comprehend. A person could spend their entire lifetime trying to parse all of this data and only skim the surface. So what we need to do is we need to look to artificial intelligence, or a form of artificial intelligence called machine learning. So I know a few of you will probably know what machine learning is, but if you don't, machine learning is looking at these kinds of mathematical algorithms that we train to kind of to pick out different things that we would in pattern recognition and to mimic human learning. So we're using maths to basically pull out patterns and pull out trends of these really large data sets. So this is what I'm doing in my first project. I'm using these mathematical algorithms and I'm using it on data that we already have, so that we can get more data in the future and better data in the future. So a rough outline of what I did was I got all of the old 1CBL supernova data. So I've gone back all the ways maybe to 2002 and gathered all this data that we have about how the brightness is changing of these different types of supernovae. And I'm able to tell this model what is a type 1 CBL supernova. So I showed the model. I'm like, this is what a 1 CBL looks like. This is what a different type of supernova looks like. So it's able to tell me, yes, it's a 1 CBL, or no, it's not 1 CBL. So I use all this data, I train it up, and then I use the model on something that's unseen. So there could be a supernova happening exactly right now, and if I have the data, I can run my model, use the data, run my model, and it can tell me, yes, it's a 1 CBL, no, it's not a 1 CBL. And then we can ask other people in observatories to follow up this type of supernova, to get more data on it, because in order to be able to follow up the supernova, you need a scientific case. So I can't go up to an observatory right now and say, hey, I want to look at this part of the sky, I want to look at this transient. They're going to ask me, why do you want to do it? Do you have any scientific backup to look at this certain type of supernova? So I always have to have this kind of backup to justify why I want to look at a certain thing, because telescopes are very expensive and observing time is very limited. A lot of people want to look at different things, so you need to have a good science case behind why you want to do what you want to do. So what kind of information do I need to feed this model in order to for it to tell me and distinguish between the different types of supernova? So you can see in the blue shaded box here, this is where we're most likely to see a gamma-ray burst in the really early days. So that's about 0 to 5 days is when we're going to see a gamma-ray burst emission. So you can even see in this certain type of 1 CBL, we didn't get data before 5 days. So we've obviously missed a gamma ray burst if it did happen. We don't know if it's happened or not. So we need to get the data within this blue box. So what I decided to do is, well, I need to get early time observations. I need to be able to know whether or not it's this certain type of supernova really early. So what I did was I was able to get the magnitude rate of how fast a supernova is rising in brightness, how quickly it's getting brighter. What I noticed about type 1 CBL supernovae is that they rise or they get brighter much quicker than other types of supernovae. So this is my distinguishing factor that I'm going to tell my machine learning to look for. So I calculated this magnitude rate by just getting the difference between brightness over time, and I was able to calculate that and feed that into my machine learning and give it a quantitative description into how a supernova is getting brighter. And what I found was, in my initial results, I was able to train models using supernovae that were detected by a telescope called P48 in the Zwicky Transient Facility. So this is a facility that's run by Caltech in California. They have they've brought all of their data publicly available, so any of you could go on and get this data. And I went through tens of thousands of supernovae, was able to tell my machine learning, yes, this is what a 1A or 1B or 1C looks like, and this is what I want you to tell me. I want you to tell me if you see this 1CBL supernova. What I found was my machine learning can potentially identify up to 50 to 70% of the entire, what we think is the actual rate of 1CBL supernovae. So if we put this into numbers, we have 20, we think that there could be 100 happening per year, but we're missing them. We're only classifying 20 of them. So if I implement my machine learning with all of the different telescopes that are happening right now, I can increase these 21 CBLs being detected per year to 70. And that will increase the probability of us detecting another gamma-ray burst and supernovae happening at the same time. So that is what I've been doing for the last maybe 2.5 years, and I'm going to be publishing my paper on my results on this very soon, hopefully. So now I am going to talk about gamma rays, more about gamma rays, less about supernovae. So at the moment, we have a lot of gamma ray telescopes up in space, but you can see here that we have a massive gap from 2025 to 2029, where there's going to be very few gamma ray burst telescopes up in space, which is a big problem because we could end up having a year or two where we'll have no gamma ray telescopes or detectors in space, and we won't be able to detect gamma ray bursts properly. So what a solution that the astronomical community has come up with is to build smaller, cheaper, and faster to launch satellites called CubeSats. So CubeSats are these 10 by 10 by 10 centimeter cubes, all stacked on top of each other. So AirSat-1 is a satellite or a CubeSat that we have developed here in UCD, and it stands for Educational Irish Research Satellite, and 1B the first. So we have two U's in AirSat. So you probably think that satellites are quite big. AirSat is probably the size of a 2-liter milk carton. So it's tiny. It's probably the size of my own laptop in my hand here. And it weighs about 2 kg. So it's really, really small. It was really cheap to build, very efficient, but it is able to do 3 different experiments. We have 3 experiments on board the satellite, even though it's so small. So these kind of satellites are perfect for students learning how to operate a satellite, build it, the electronics, the educational outcomes from these satellites are phenomenal. So on our satellite, as you can see here in the bottom right, we have 3 experiments on board. We have a GMOD, which is a gamma-ray module or a gamma-ray detector. We have EMOD, the MBio module, which provides a protective paint. So it's protective paint for satellites going towards the sun to keep it cool and going away from the sun to keep it warm. So there's a black paint that keeps satellites warm and a white paint that keeps it cool. And then we have wave-based control, which is a software-based experiment. So the main area of the satellite that I'm going to be focusing on today is the gamma-ray module. So just to have a look inside the satellite, you can see that we have a checkerboard-like pattern here on the top. That is the MBIO module. So those are the samples of the paints that we're testing in low Earth orbit where the satellite is orbiting around Earth. Inside the satellite then we have a silver box, which is the gamma-ray detector. And then at the bottom is our antenna, which we use to talk to the satellite and send commands and receive all of the information from it. So you can see a better picture of the satellite there on the right. See the solar panels, which charges the battery on the sides, and then the MBIO module up on the top. So before I go into the nitty-gritty about the satellite, I just wanted to show this is a really exciting time for us. Not last December now, it's December before last. So on the 1st of December in 2023, AirSat was launched from Vandenberg in California aboard a SpaceX Falcon 9 rocket. So once it was high enough altitude for our orbit, it was pushed out of this rocket and it waited 45 minutes before it deployed antennas and we could talk to it for the first time. So this video is actually really cool because this is shows the satellite's first moments in space. So if you look really closely in the corner, you can see the satellite being pushed out on a springboard out from the Falcon 9 rocket, which is super cool. So next is our ground station and operations here in Beach Hills. So this is our antenna. So it is located directly above us on the roof, and it is able to track and communicate with our satellite as well as get all of the information from the satellite down to us. So this is connected to our computers here in UCD, and you can see on the right hand side this is our operations center. So we have two computers which are connected to our ground station, and we're able to remote into these computers so we can actually operate the satellite from anywhere in the world. I can operate these computers straight from my laptop and thus satellite, which is pretty cool, and it's really nice that I had to operate on Christmas Day and I didn't have to be here in Dublin, I could be home in Cork. So next is GMOD. So this is exactly what GMOD does. So again, GMOD stands for the gamma-ray module, and it operates on the principle of scintillation. So scintillation is a process that happens when a certain type of light hits a crystal and it produces visible light. So inside the GMOD is cerium bromide crystals. So when a gamma ray hits these cerium bromide crystals, it produces a flash of visible light. And this flash of visible light, due to the beauty of electronics, we're able to convert this flash of light into a digital signal using photomultiplier tubes, which are located under the cerium bromide crystals. And that signal is then sent down to us on Earth, and it is registered as a count. So down in the bottom, you see the black kind of graph here is what a gamma-ray burst a gamma-ray burst light curve looks like in gamma rays. So you can see it looks very different to the supernova curve that I was showing you a while ago. So instead of a brightness, we're counting the number of gamma-ray photons that hit this crystal per second. So you can see here that's a very bright gamma-ray burst. It's almost 10,000 gamma rays per second hitting that detector, which is really cool. So in regards to our own operations, so it's very hard to get the Gamma-Ray module up and running because we have to take into account this area above South America called the South Atlantic anomaly. So this is an area where this region called the Van Allen belt, so where a lot of radiation is accumulating and hitting the atmosphere of the Earth. And it's also very energetic. It's also a problem at the poles as well. So you probably all know, you've hopefully seen the Aurora Borealis here in Ireland this year. And the Aurora Borealis is produced because cosmic rays or radiation is hitting our atmosphere. So this happens a lot at the poles of our star, the poles of our Earth. So that means there's a lot of radiation, and that means that it could potentially damage detectors on satellites. So any satellite, not just AirSat, will have to turn off their gamma-ray detectors when they go through the South Atlantic anomaly because it could damage and completely ruin the detector. So what we had to do is we needed to figure out, okay, where is the safest place to turn on the gamma-ray detector, and where is the safest place to turn it off? because if we left it on the entire time and it went through the South Atlantic anomaly, our detector completely shuts off to protect itself. So we wanted to keep the detector running for as long as we possibly could. So we were able to map this out, see where the detector would reset, would overload, and turn off to protect itself. And we were able to map the Earth. So we now know, and we were able to set timers on board the spacecraft to turn on and off where the regions of really high radiation are to protect itself. So we don't need to manually go on and turn it back on ourselves. It turns off when it needs to and turns back on then. So it can be running for weeks at a time, which is really handy. And when we got that up and running, we were very lucky to detect our first 2 gamma-ray bursts last August. So since these are the first 2, so we actually detected them both on the same day, and they were one of each type of gamma-ray burst. So it was like a Christmas present in August. So we first got a merger, GRB, which is very skinny and lasts very like a millisecond there. And then we have a collapsor GRB, which is much fatter and much longer, lasts much longer. So since then, we've detected 8 gamma-ray bursts using AirSat, and we were able to send a notification to NASA. So these are general circular notices. So whenever anything of note is detected by the astronomical community, let's say we've discovered a new gamma-ray burst, we've discovered a new supernova, we need to let the rest of the community know as soon as possible because they're transient. They happen really quickly. We want everyone to be able to take as much data as possible. So we send out these notifications to tell everyone, hey, there's a supernova, there's a gamma-ray burst happening at this point in the sky. So this was really cool, and a lot of notable researchers were citing us and were asking us for help. Which was a really cool thing to happen. So that is, I think, it for me. Thank you so much for listening, and I'll take any questions.